Okay, so this is a simulation of the toroid. Now, if you are interested, you can download this simulation from this site. I will write it down. This is the guy that's preparing these simulations. Now, if you see these yellow ones, this is the current. The current is running in this like this around the toroid. And as you see, most of the magnetic field lines are inside our toroid. But of course, close to these currents themselves, there are all these loops. I mean, around all these loops, there should be some small circular ones because you see, although this is a toroid, there are many gaps between the wires. So among those gaps, some of the magnetic field lines will be escaping from the interior. Now, if you would rotate it a bit, so this is our toroid. You see there, although in a perfect toroid, outside there is no magnetic field. But this is not a perfect toroid. It's a toroid with a finite number of turns. There are many gaps between the wires. So you see all these magnetic field lines that are kind of escaping from the toroid. If you increase the number of turns, so we expect the external magnetic field lines to get smaller. So this is the increased number of magnetic field lines. Let us increase it even further. This is the maximum. So you see, in this case, well, there are still the gaps are large. But you see that most of the magnetic field lines are still inside. Outside, there are not so many magnetic field lines. There are some escaping. This is how the magnetic field lines of the toroid looks like. Now let us look at the solenoid. No, this is the toroidal solenoid. Let's look at a linear one. This is the magnetic field lines of a solenoid. So you see that most of the magnetic field lines, they enter from one side and they leave from the other side. So this is the south pole of the magnet. This is the north pole of the magnet, if you just imagine it as a magnet. Also, in this case, there are magnetic field lines that are leaving from the sides because there are all these gaps. Let us increase the number of turns. Now, there are still gaps. So there are some magnetic field lines escaping. All these ones are escaping magnetic field lines, but nevertheless, most of the magnetic field lines escape from the edges. So this is from the sides, from this the region which is far from the ends of the solenoid. The number of magnetic field lines, the density of the magnetic field lines at these points, they are very small. Now we can also look at, let's say, loops. So here we have just two loops. Let's increase the separation a bit. So it's still, when you have two loops, they are both carrying currents in the same direction. Most of the magnetic field lines still just go through both of them rather than just getting out. Of course, if you increase the separation, there will be more magnetic field lines escaping from the in-between. So you see what's happening. These, the magnetic field lines, they try to go out and come back in, but as you increase their separation, these magnetic field lines that are trying to escape, they go further and further, and eventually they just combine with the returning field. So if you follow this magnetic field line, it comes from the bottom loop, tries to go out, then comes back in, then it just turns around and closes the loop. So this is what is its return path. Now, as you increase the separation, they just combine together and form a closed circle. You mean this one? So we have two loops, one on top of the other one. In this one, it is turning, let's say, in this sense. In the other one, it is turning in the other sense. So as we had discussed, in this case, the magnetic field lines, they will enter from the top, but they will not be able to go to through the bottom loop, and they will just close the circle like this. This is what we had also discussed. Well, those are the solar flares. Is that what you mean? This is a magnetic field line. The charges are well, you cannot really see it from here, but the charges are mainly following the magnetic field lines in this case. Since we already know that the charges, they tend to go make circles around magnetic field lines, they don't go away from the magnetic field lines. Now, as the magnetic field, if the magnetic field line for some reason is moving, the charges will also follow it. So this is over here. Well, it's somewhat more visible in this image over here. So you see there's this loop, almost a loop. This is a magnetic field line. So you can actually see the magnetic field lines there. Yeah. This is a magnetic field line. Well, what happens when, in the previous simulation, we saw what happens when two magnetic field lines, they come together. They just, the magnetic field lines do not break, but they can combine. If they combine, you are mainly changing their configuration. So at the point when there's such a rapid change, well, what does the charges do? They were following the magnetic field lines, which no longer exist. It looks like an explosion. Any questions on these, on magnetic field lines? Now, the site where you can download these simulations is this one. Nothing. Now let's discuss a bit about the magnetic materials. Now, one important lesson that we should learn in this chapter is that if there are currents, there is a magnetic fields. And in fact, magnetic fields are only created by currents and nothing else. So if something is creating a magnetic field, there is inevitably some current running through it. It can be a macroscopic current, it can be a current that runs from one region to the other region, or it might be a local current, but there has to be a current there. Even in magnets, there are currents there. It's the currents that are creating these magnetic fields of the magnet. Now, what are the microscopic origin of these currents is nothing but the electrons. So if you imagine an atom, it has electrons which are moving. In a conductor, they can move anywhere in the conductor. In an insulator, they are attached to the atom, but nevertheless, they are moving around the nucleus. So electrons are always moving, and hence, they create a current. Currents are everywhere. And this current can create a magnetic field. Current, well, this current will reflect itself as a magnetic dipole moment, and hence you can have a magnetic field. Now, of course, the atom doesn't only have a single electron, yet it usually has many electrons. And even if you think of the hydrogen, you don't have a single hydrogen, you have a hydrogen molecule which has 2 electrons. And in general, those electrons, they just move in such a way that the net magnetic field of most of the atoms is 0. The net is 0. Now, there is another factor that's creating a magnetic field. Now, the electrons have what we call a spin. Now, historically, when we first discovered, what we discovered was, now up to now, the magnetic force only acted if there were charges moving. If the charges are at rest, there is no force acting on them. But if you do this experiment on an electron, if you do a precise enough experiment, what we observed was even if an electron was at rest, there was a force acting on it. Well, we already know that, for example, although the electron is a single charge, if an object has a magnetic dipole moment, it will feel a magnetic force even if it's not moving. If you just imagine, for example, a single magnet, 2 magnets, each magnet is nothing but a magnetic dipole. They have a magnetic dipole moment. And if you bring 2 magnets together, you already know what happens. There is a force over there, although they are not moving. If there is a magnetic dipole moment, there will be a force. So the electrons have a magnetic dipole moment even if they are not moving. So these are the 2 sources of the magnetic moments of a given material. They can have a spin due to the spin of the electrons, they can have a magnetic moment, or due to the motion of the electrons, they can have a magnetic moment. Now, of course, for most materials, these magnetic moments, they just sum to give 0. Mm-hmm. Okay, so let us give a simplistic description of the electron, which you should forget the moment that you leave this class. You can just imagine, classically, an electron, the spin of the electron, as if we have a sphere with the charge minus E, and it is rotating, such that it has an angular momentum. Etc. Now we can model the electron as if the total charge is on the surface or distributed over the volume uniformly, etc. In any case, you will have a moving charges going around in circles. They will have a magnetic dipole moment. And you can just sum them up to obtain the total magnetic moment of the electron. Of course, the total magnetic moment of the electron will be proportional to the angular momentum. So, even then they have an angular momentum. I mean, the reason why I told you that you should forget this description is not, an electron is not a sphere, it's not a rotating sphere. The spin is weird, and it's a weird phenomena that you will study in quantum mechanics. The only thing we know is that it exists, it has a spin, and it's not such a rotating sphere. But classically, at the level of this course, we can still imagine it as if it's a rotating sphere. And hence we can understand why it has a magnetic moment. Now, so we have all these sources of magnetic moments for the, let's say, the orbit of the electron can contribute to the magnetic moment. The spin of the electron can contribute to the magnetic moment. Now, the choices are the total magnetic moment might be 0. In this case, we call such materials diamagnet. I mean, we will discuss these diamagnetic materials in more detail after chapter 29. Just remind me. And we can have the total magnetic moment of the atoms or the molecules might not be 0. And these are what we call paramagnetic materials. Well, if you consider a paramagnetic material, it's mainly made up of atoms or molecules which have their own magnetic moment. But on the average, they will be just distributed randomly. So the total magnetic moment of, this is the total magnetic moment of the atom or the molecule. Yes. So if you consider a paramagnetic material, it's mainly made up of many atoms or molecules that have some total magnetic moment. But these magnetic moments, in general, they will be just aligned randomly. If one magnetic moment is pointing in this direction, another one will be, the one next to it will be pointing in this direction, the one next to it will be pointing in that direction, etc. So they're all randomly distributed. And so the total magnetic moment of the material itself will be 0. So you take a paramagnetic material, so if this is your material, this is the direction of the magnetic moment of one of them, this is the direction of the other one. They're all randomly oriented. So they just sum up to give 0. They will have no magnetic field. They will not create any magnetic field on their own. This is if B is equal to 0. Now we know how the magnetic dipole behaves under the influence of a magnetic field. So if you put a magnetic dipole in a magnetic field, it will feel a torque. And since it feels a torque, it will a torque that will try to align the magnetic moment in the direction of the magnetic field. So if you put it in a if you take the same material and put it in a region where you have a magnetic field, a non-zero magnetic field, it will just try to align these dipoles. So the dipole will be mainly distributed something like this. They can still be somewhat random, but they will have a tendency, they will try to rotate in the same direction as the magnetic field itself. But we have seen what a magnetic, so this will just mean that my substance as a whole, let's call it M, no. My substance as a whole will have a net magnetic moment. But if it has a net magnetic moment, it also will be creating its own magnetic field. So you have this magnetic field, you put this material in that magnetic field. So the net magnetic field will be the external magnetic field that you apply plus the induced magnetic field. And now this is just like a magnet. It has the magnetic dipole moments pointing preferably in the upward direction. It will create its own magnetic field, which will be, okay, inside the material it will be pointing upward, outside the material it has to close down. Because now my material itself has a magnetic moment. And this also means that in the material, the magnetic field lines will be, the magnetic field will be stronger because I have this external magnetic field plus the magnetic field that is induced by these magnetic dipoles. They are both pointing more or less in the same direction. Outside, they will be pointing in the opposite direction, so there will be more magnetic field lines inside than outside. Now, if you would plot the net magnetic field line in the presence of a paramagnetic material, this is my paramagnetic material. Very far away, the magnetic field lines will be uniform. That's the applied magnetic field. As they approach, well, we know that the magnetic field inside is stronger than is outside. It just means that the magnetic field lines are denser inside than they are outside. So what this ferromagnet does is it behaves as if it is attracting the magnetic field lines. No, this is paramagnetic. This is how they will look. Of course, if you are sufficiently far away, they will not be influenced that much. No. B total. This is how the magnetic field lines will look like. Now, what happened here is we had this paramagnetic material, which are just materials made up of atoms or molecules which have a net magnetic dipole moment. Since they have a net magnetic dipole moment, in the presence of an external magnetic field, they will align themselves in the same direction. They will try to align themselves in the direction of the magnetic field. So I have a system which has a net magnetic dipole moment. Well, a system that has a net magnetic dipole moment will have a net magnetic field. It will create a magnetic field. And we already know what kind of a magnetic field a dipole creates. So this is the magnetic field lines. These two are the magnetic field lines of a dipole, a magnetic dipole. This is what we call the induced magnetic field. Initially, there is zero magnetic field because the magnetic dipoles are just oriented randomly. They just sum up to give zero. When I put them in a magnetic field, the magnetic dipole moments, they try to align. And since they are aligning, they will not be canceling each other, not completely at least. So I will have a net magnetic field, net magnetic dipole moment. Well, this net magnetic dipole moment is creating this induced magnetic field. No? You see, inside the external magnetic field is stronger. It is not canceling it. It is adding to it. Outside, because this is a dipole, the magnetic field outside this dipole will be in the opposite direction. And hence the magnetic field lines, the intensity of the magnetic field outside will be smaller. This is external. Now, how much magnetic field will be induced? Well, it will depend on the permeability of the material, magnetic permeability. This is just like the dielectric constant. This is another constant of your materials, which characterizes how the material behaves under the external magnetic field. Any questions on this? Most of the materials are paramagnetic. Well, you see, there's one more thing. How we distinguish the two, well, the total magnetic moment of the molecule or the atom making this system. It can be either zero or non-zero. So those are the only two choices we have. One of them we call diamagnetic, the other one we have the paramagnetic. Then comes the ferromagnetic materials, which are, in fact, in this classification. Okay, you see, do you know the chemical symbol of iron? Now, ferromagnetic materials are just materials, in a sense, historically speaking, at least they were named after iron. They are materials that behave like iron. Iron is one of the paramagnetic materials. We have just like 4 or 5 elements that are ferromagnetic. Now, what distinguishes now in ferromagnetic materials also the atom has a net magnetic dipole moment. But what distinguishes ferromagnetic materials from paramagnetic materials is that these magnetic dipole moments, neighboring magnetic dipole moments, when we were discussing paramagnetic materials, we said that neighboring magnetic moments, they are just aligned randomly. In ferromagnetic materials, neighboring magnetic dipole moments, they tend to align in the same direction. So this is what separates the ferromagnetic materials from paramagnetic materials. So this is what gives ferromagnetic materials its distinctive characteristics, in the sense that, for example, when you look at a paramagnetic material, you take a paramagnetic material, when you bring down a magnetic field, a magnet close to it, an external magnetic field, it will be magnetized. It has a net magnetic moment. The sample as a whole has a net magnetic moment, but when you remove the external magnetic field, all this net magnetic moment will just disappear. It will not make a permanent magnet. I mean, they just align because of this external magnetic field. That's it. When you remove this external influence, then they will again go back to their random orientation. Now, in ferromagnetic materials, you can just think of them as the paramagnetic materials is like group psychology. I mean, if somebody does something, everybody tries to do the same thing. But when the external influence disappears, when the group separates itself, disperses, everybody does random things. Now, this ferromagnetic materials is like, they say, close friends. They don't want to let go of their friends. They always stick together. But of course, even close friends, I mean, you can make groups of 5 people, 10 people, but not hundreds of people. So in these ferromagnetic materials, if this is your ferromagnetic material, here you have a couple of friends. They are pointing in the same direction. And next to it, you get another couple of friends pointing in the same direction. Here they point in the same direction, etc. So you have regions in these ferromagnetic materials which point in the same direction. But different regions might be pointing in completely different directions. So these are the directions of the magnetic dipole moments. Now, all of these regions are what we call domains. This is one domain. Now, the domains can be huge. At at the level of 1 millimeter. Well, compared to the atomic size, that's a huge number. That's a huge distance. So all the atoms in this domain, their magnetic dipole moments, they are pointing in one direction. In the neighboring domain, they are pointing in the opposite, in some other random direction. So again, in the absence of any external magnetic field, if you just pick up one piece of iron, it will not have any magnetic property, because it just has all these domains pointing in random directions, and hence the net total magnetic moment of the iron that you pick up will be just arbitrary, will be just zero. Since the total magnetic moment is zero, there is no magnetic field created by this ferromagnet. But if you put them in an external magnetic field, well, you see, in this region, why do we have the domains to start with? Let's just imagine that we pick up an iron, we heat it up. Now, heat is just random motion of the molecules or the atoms. Motion, it can be translational motion, it can be rotational motion. So if you heat up a material, it will be randomly, if it's a liquid or a gas, each of the atoms will be moving around randomly. If it's a solid, they will be just vibrating randomly. And in any case, they can be rotating randomly. If they are rotating, their magnetic dipole moment will also be rotating randomly. So you take this material, heat it up to a very sufficiently high temperature, so all of these magnetic dipole moments will be rotating randomly. They don't have a definite orientation. So above this critical temperature, which is called the Curie temperature, these domains, they just disappear. So above this Curie temperature, the domains, they just don't exist. Now, as you cool it down, below some certain critical temperature, these neighboring atoms, they just start to align their magnetic dipole moments. So you are cooling your material. As the material gets below this critical temperature, let's say the magnetic dipole moment at this point, and its neighbor, they just align. At this point, well, this point, it has no idea that they have aligned in that direction, so it will just align in some other direction, those two neighboring atoms over there. At this point, well, it doesn't know about these two alignments, so it will just align in an arbitrary direction. And once they start to form these groups, have you ever watched how the crystal forms as you cool down water? You can try it. I mean, the crystals, they start from a point and they just start to grow. This is what's happening over here, exactly the same phenomena. In this case, it's not the crystallization, it's not the transition from liquid to solid, but it's from a completely randomly oriented magnetic dipole moments to regions of uniform orientation. And these regions, once they start to form, they grow. So once we have these two align, they will just convince their friend to align with themselves with these. And as this domain is growing, this other domain will also grow. And similarly for this one. And eventually, they just collide. Let's say their boundaries collide. They just hit the other domain, and that's where it stops. Yes. In a sense, they have crystallized. So here we have a domain with one orientation. Here we have another domain with another orientation. Here we have another domain with another orientation. And you will have many randomly oriented domains. Well, you see, neighbors only speak with each other. I mean, this atom over here, for example, it speaks with its neighbors, but it doesn't know that there are all these other atoms over here. It will not be so much influenced by them. So the size of the domain doesn't really matter in that sense. It's only at the boundary. So you see, there is one domain over here, another domain over here, or let's say you are just two separated. There is the second row domain, there is the other third row domain, and the third row and the fourth row is another domain, let's say. They are in the same domain. And then the second row tries to convince the third row to convert. Well, the fourth row also tries to convince them, they convert, so they don't really feel any necessity to convert, they just stay where they are. But then I push the third row telling them that, okay, you should convert to the second row, second domain, the domain of the second row. Well, that's an external effect. That's me. Or in this case, we apply an external magnetic field. Well, this third row doesn't really care about which domain they are in. They just happen to be in the same domain as the fourth row, so they just stay there. But now there's an external influence. Now, if there is such an external influence, what happens is the third row will be converted to the domain of the second row, because they don't really have any motivation to be in the second row or in the fourth row. They don't really care. With this external influence, they will be converted. Just like here, when we apply an external magnetic field, some of the domains, okay, the domains have a magnetic dipole moment. We have this external magnetic field, so there will be a torque acting on these domains. Some of the domains as a whole, they might rotate, but most of the time, the magnetic dipoles right at the boundaries, they will be converted. Because now, right at the boundary, if you imagine an atom over here, these ferromagnetic materials, they always try to align with their neighbor. But if you are at the boundary, it has two different kinds of neighbors, so it doesn't really know what to do. So with an external influence, it's easy to convert them. So what happens is, the domains that are in the direction of the external magnetic field, they start to grow. And the domains that are in other direction, in opposite direction, let's say, they tend to shrink in size. So the domains that are in a given direction, they are growing. Domains in the opposite direction, they are shrinking. So you end up having a net magnetic dipole moment. So you apply an external magnetic field, and this just becomes, let's say, some huge region where we have magnetic dipoles aligned in the same direction as the external magnetic field. Here we have another region. They will also be aligned more or less in the same direction. Here we might have some small regions which are pointing in opposite directions, etc. The regions that are pointing in opposite direction will shrink. The regions that are in the same direction will just grow up. Now there's a huge induced magnetic field. So now we have these huge magnetic moment of the ferromagnetic materials. So we apply an external magnetic field. The domains in the direction of the applied magnetic field, they grow. And the domains that are pointing in the opposite direction, they just shrink. Most of them will be pointing more or less in the same direction. Okay, we are running out of time. Okay. You will not see it. You will, but the others won't. Okay, so we have all these domains pointing in the direction of the magnetic field. They will grow. Okay. So this is the external magnetic field. Let's say this is the total magnetic, the magnitude of the total magnetic field in a sense. So what will happen is they will just grow. Well, of course, it can only grow until all the domains are more or less pointing in the same direction. So as the external magnetic field the magnitude gets larger and larger, there will be a point where it saturates. Now remember, these are materials which want to have their neighboring magnetic dipoles pointing in the same direction. Before, let's say, this domain of the third row, they didn't have any preference. Now, after an external influence, they made the choice. They converted. Now, once they are converted, and let's say you remove the external influence, they still don't have any motivation to convert back to their original domain. So when you remove the external magnetic field, what happens is that the total magnetic field will diminish, but it will not go to zero. Even if you remove the external magnetic field, the domains that have grown, they will just stay where they are, most of them. So even if the external magnetic field goes to zero, so we started with a material that has zero total magnetic field. Let's say induced magnetic field. It was made of domains, and the orientation of the domains were just random. Then we applied an external force, external magnetic field. Now this external magnetic field, it caused the domains in the direction of the external field to grow, or rotated the orientation of some other domains. So as you increase the external force, the induced magnetic field becomes larger and larger until it reaches a saturation point. Now at this point, almost all the domains are pointing in the same direction. Then you remove this external influence. But if you remove the external influence, the domains that have been grown, they don't have any reason to change their direction, or the dielectrics, the dipole moments that joined one domain, there is no point for them to go back to their original domain. So they will just stay where they are. But if they stay where they are, the induced magnetic field will more or less stay the same, because this induced magnetic field just depends on the net dipole moment. We oriented them by applying an external magnetic field, so they are all oriented in the same direction. When we remove this external influence, they will still stay oriented in the same direction, more or less. So this is where you have a permanent magnet now. They will just stay there. Since they have a net induced magnetic field, or net induced magnetic moment, mu, total magnetic moment, they create a magnetic field, and hence they can exert forces. This is what you call a magnet. These are, in fact, what you are also sticking on your refrigerators. Now, of course, you can revert the direction of the external magnetic field. If you revert the direction of the external magnetic field, then what's your, here you grow, you feed it the domains in one direction. If you revert the external magnetic field, you will be feeding the domains in the completely the opposite direction. So that will just lower this induced magnetic dipole moment. It will get small. Eventually, the total the magnet will just disappear. And then you start to saturate it again in the opposite direction this time. And again, if you just remove the external magnetic field, when it reaches the saturation, what will happen is that all of them are pointing now in the opposite direction. When you remove this external magnetic field, again, it will not go to zero. They will just stay where they are, more or less. And if you, again, apply an external magnetic field in the original direction, this is what this will be the trajectory of the induced total magnetic moment of your material. This is what's called the hysteresis curve. This is how from the ferromagnetic materials, you can create these permanent magnets. The only thing you have to do is just apply an strong enough external magnetic field so that you have a large total induced magnetic moment at some time. And then if you remove this external force, it will just stay there. And you have a permanent magnet now. Now this hysteresis you will see in a few areas of physics. It just means that if you look at here, you see the induced magnetic dipole moment doesn't depend on the external magnetic field only. It also depends on the history. If the external magnetic field is zero, well, the total induced magnetic moment can have a large positive value, can have a large negative value, or it can even have any value in between. It depends not only on the external magnetic field, but also on the history, how that material was created to start with. History. Now, in paramagnetic materials, this is not the case. If you know the external magnetic field, you know the total magnetic dipole moment of the material. There's a one-to-one correspondence. It doesn't depend on the history. In ferromagnetic materials, it does depend on the history. Okay, any last-minute questions before the exam? Well, for ferromagnetic materials, the domains are already there. Now, why do they form at a very high temperature? Well, we will have to leave. Arbitrary. They just choose their direction. Initially, they choose it arbitrarily, if there is no external influence. Well, okay. We will have to empty the classroom soon. So if you have any questions, we can just discuss out of the door.